Okay. So that kind of covers the structure in terms of just the arcs. Now we're going to look at the parameters and also related to that, the relationships between nodes. So you know what the parameters in a CPT typically look like at this stage. You've got lots of rows which are based on all of the combination of the parents. That's not the only way to think of the relationship between the parents and the child. So let's look at it that way for now and see what we can produce. So we say, we've got our CPT and we say we need numbers. So we go to our experts and say, okay, how do we approach that process of getting the numbers from them? So we can just ask them. Sometimes it's really simple. There's well-known sources of information for what these parameters should be. Use it when you can do that. That's fantastic. Sometimes it's obvious to you, as in it'll be a common sense kind of number that you need to put in there. Some of those numbers, for instance, from yesterday, you knew that they had to be 1 and 0 because it was just a constraint of the problem. So that's easy. Try and knock out all of those simple probabilities first before you then go to your experts. Don't waste your experts' time with wasting time on numbers that are really trivial to kind of elicit. Now, in the context of this software, in terms of the BARD software, we want to be trying to build in as much of the constraints and the ideas behind the templates straight off from the bat, and we only get the users to elicit just the key pieces of information. So a big, just to digress a little bit on this because I think it's a key point for the BARD project. If you're getting users to elicit CPTs, which are larger than about maybe 4 or 5 rows or something, you've done it wrong. Okay, so you want to be working out what the structure is. That's absolutely essential. You want to work out what that structure is and then only elicit the parameters that are needed relative to that structure. Okay, so if it's an OR relationship and it's a noisy OR, which we'll see in a moment, then you just want to elicit the parameters of the noisy OR. And you don't want to describe it as a noisy OR to the users. You want to present it in a much simpler way. Okay, so you've got direct elicitation for those numbers. You can also elicit individual probabilities just by eliciting odds. So this is very useful for when you've got really large numbers. You can say, well, instead of saying 0.000001, you can say it's 1 in a million. Okay, so you've got qualitative assessments. This might turn out to be useful for this project. So you want to say, instead of asking for a specific number, whether it's 0.8 or 0.85 or 0.851, doesn't really matter. You can probably just say, oh, well, this is a very high probability. And then you can map that in some way. And this might be something, if you've got lots of users entering in this kind of qualitative information, you might actually analyze that afterwards and say, well, actually, people mean this when they say this. So we'll map it in this way. If you're eliciting continuous values, which are probably, or continuous distributions, which probably won't be doing here, but there's a couple of different methods that you can use if you are doing that. So you can elicit basically the quantiles of that distribution. So you can say, well, what's the median value? What's the 25th percentile? What's the 10th percentile, and so forth. And you keep eliciting those to the level of accuracy that you need. And you do this using bisection basically to save time. So you don't want to start off with every percentile and elicit all 100 of them. You start off with 50th, 25th, 12th, 12.5, so forth. And then you only elicit to the level that you need. And then you've got a reasonable level accuracy resolution for your distribution. You probably won't do that for this project. Okay. Something that you will, yeah, sorry?
Just back to your comment that you should keep the secretary small.
Yeah.
We won't be doing any of that. We're the end users.
That's right, but you need to be thinking in terms of what the end user needs to be doing. So you need to be building these models.
That's what I'm saying. So
yep.
No, not so much the model.
Mm-hmm.
We won't be building the model either, right?
You won't be building.
The end users using
Yeah, you won't be building the specific models that the end users use.
Are you suggesting we build the software to try to encourage them,
Yes.
or build that into the training?
No, it shouldn't go. Training should be the last resort.
So you can build it into the software so that we encourage small CPTs?
Yeah. Yep. So you're going to be, it's not going to be just you guys deciding how this works. There's a whole, support team kind of, investigating the best ways to do it.
We're not the people who are going to build the network, right?
No, but you're building the software that the end users are going to be using. So, yep.
You're suggesting we build that software to actively encourage smaller...
Yep.
And the software generates the billion. So
Yeah, I know that, but we've got to somehow get the facilitator, or the facilitator to try to reduce the size of the...
Well, it'll be, you've got to be thinking of the combination of the two, yeah. But I would hope that you think like a user. So I would hope that you identify almost as a user of the software, so that you've got a very good sense of the usability of the software. Because otherwise you're going to create things that you don't know what it's for. And you're going to have users whose intentions and objectives are different to yours, and that's a recipe for disaster. Yep. Okay. I've got tangled up here. Okay. Something that you will make a lot of use of, not necessarily in this form, but in some form, are visual aids of some sort. So you don't necessarily need to shy away from the numbers. I think it's quite okay in a lot of cases to, particularly if you've got key parameters, to then focus on the numbers. But where it doesn't matter, it's probably best to go to a visual aid of some sort and get them to elicit something that's approximately true. So this is a little bit like the verbal cues. You want to be, you don't need to say what a specific number is. You can say it's just very high. Sometimes people prefer to do that visually and just say, well, it's, this much bigger than this, and just do it that way. Okay, so there's lots of other kinds of techniques that you could use here. Usually the techniques are domain specific, so they're probably not going to be, of great value to you in terms of that. But you should be thinking in terms of general visualizations and approaches to representing the data that would be useful. So this is an example of elicitation that was done by Anne quite a few years ago now, I think, with the New South Wales RFS. And so they were trying to work out the consequences of certain decisions and the impacts of various fire scenarios on houses in various areas with the RFS. So what they did was they got a bunch of monopoly houses and they put it all into the centre, and then they labelled out the different scenarios, the different outcomes, and said, okay, how many houses are going to be lost in this scenario? And so everyone, the group, basically pushed a whole bunch of monopoly houses over to how much they thought were going to be lost in this scenario versus the other scenarios. So that was really useful. One thing that's useful about it is that it's fun. It's got that element of play that I think is going to be important in this. So the idea of making it a little bit like a game. And the users were engaged. They submitted. They were able to elicit things from those participants, which were actually useful pieces of information. Everyone was kind of keen to get in and have their say on how things worked. If you resorted to dry numbers in those cases, then you're going to get probably good estimates. Particularly if you're using Delphi, you're going to get good estimates most of the time. But you'll get less engagement, less research from the individual users and so forth. Okay, so this is actually something that I wanted to demo. I might try going over there. So this is an example of the verbal cues that we talked about. So we created some software a little while ago now, probably 9-something years or something, that we started working on this software, and we've kind of iteratively worked on it over those 9 years. This is something that we created for what at the time was called the Department of Sustainability and Environment in Victoria, but which is now called the Department of Environment, Land, Water and Planning, DELWEP. Basically, this is some software that they use to model the threats to species across the state. And they wanted a really, really simple interface which hid as much of the details about the Bayesian networks as possible, but still allowed the few expert users, that knew about Bayesian networks to go in and do what they needed to do. Okay, so we'll do a quick demo of this, or maybe I can get Owen to do it. Owen? Yeah? So you'll probably have to log in again. I did have it up. You'll have to, just reload because that was. Yep, did you want me to type that in? AL09?
AL09 and it's the same password.
Yep.
Is this the live version? This is yours?
This is my version, yeah.
So this isn't, we're not telling them the password?
Well, it's better not to say passwords as a general. No, hang on. No, I'll come over. Okay. So the full system that you see here is actually their system. So this is their system that they use for conservation, tracking conservation of different species. So this is just like a basic database system where they track all the species that are in different locations across the state. They list different threats that can affect those species and different mitigation actions, interventions that they can do to mitigate the different threats. Okay, so if you want to go do a search, and if you type in coastal, and you go to the coastal Muna, this one, go back. Yep. Yep. Second one, yep. Okay, so coastal Muna is just a specific species in a specific location. So we'll go to the outcomes. Yep. Yep, that one. Okay, so they can create any number of models for a particular species. What we'll do is we'll go into a particular model. We might go into the working draft one that I had open. Okay, so this is an interface for creating their network. And in some sense, this is, not quite as polished as I would have liked, but it's polished in the sense that I think we created a good product, but it had to stay within the limitations of their interface and their approach to things. So, okay, so what we've got here is all of the different things, all of the different stages basically of the model building process are kind of outlined over here. Okay, so we can go to the threats tab. Now the reason that we can do this is because we've got a particular template for the model. So we've got threats in the middle, we've got actions that can impact on those threats that are coming from the top, and we've got consequences of the threats for the species. So we start with the threats. We ask them about the threats because that then determines the rest of the network model structure. Okay, so here we've got competition and human disturbance as two of the threats that we've chosen. We'll continue on to, yep. Okay, so we have that middle layer of the network we've just specified. Now we say, okay, that constrains the problem a lot because the number of actions that they can actually carry out is in the order of thousands. But once we've determined the threats, there's only a few actions that actually impact on those threats. So we've filtered things massively. We've made the model building process for them a lot quicker. Okay, so here we ask them about the actions that are above the threats and also the consequences, the things that affect the species below the threats. So we've got the actions up here, so we can erect some signs to discourage people from going into an area. And we can, erect structures of some sort, so we could put fences up or whatever to prevent people from going into that area as well. So we've said that those are the two key actions that we want. There. Then we've got essentially the consequences, the impact on the species. So we say what we're interested in is the condition of the community. So the threats that we're modeling impacts on the condition of the communities. And those threats also impacts the area that community covers. Okay, so that's essentially the key impacts on the species that we want to look at. Okay, so if we continue. So they can build this model basically just by picking stuff from lists. Okay, so they don't know anything about Bayes nets. They know a lot about how all of these things interact in an expert sense. But they don't know, they don't even have to think about things causally because we've handled that for them. Yeah, so just get through that, yeah. Okay, so then once they've specified essentially all of the key nodes in the network, we can then do a specification of what the states are. Often these are predefined. They can leave them as the default for that particular thing. But sometimes they might want to override it and say, well, in this case, fencing, there's actually 3 fencing options. So we want to do 3 things for that. Okay, so yeah, cool. So we've got the state specified in here. And then the additional links is often something that they might be interested in doing, which is to go beyond the template structure that we've got in the back and say, actually, there's links between say actions. There might be some kind of information link or something between actions. There might be links between the asset factors. So there might be links between the impacts on the population or between threats. Probably most commonly between the threats. Okay, so if we go, essentially all of this stage was the model building. So we've built our model. They can go back and forth at any time, but they can then proceed through it linearly if they want to. That's probably the best way to start. Once they've done that, they can go to the likelihoods page, and now we're specifying parameters. Okay, so this process is still quite slow, unfortunately, but because the networks that we've built are quite constrained in terms of how they're built, there aren't an extreme number of parameters to go through. There's a lot, and it'll take experts a long time to go through, but it's not excessive. Okay, so essentially these are all the nodes in our network. And what we go through, except for the actions, basically we leave the actions off. And we go through each of these nodes and we elicit the probability table. That's all we're doing here. What we do is we try and make it as natural and comfortable as possible. So they can go through this as if it's a survey. Okay, so the online Delphi elicitation that you've been doing, hopefully doing, and we'll do this afternoon, it phrases things in natural language terms. Okay, and so you don't really have to know anything about how a Bayes net works. You just have to concentrate on the question you're being asked. Okay, so you would go through, there's the different combinations of things here. A user can ignore that if they want and just focus on the questions and keep clicking continue. Okay, so they can change these states here. So they can say, how likely is it that disturbance will be severe? And we've got the ranking of different probabilities. So they can say, well, it will certainly be severe, or it will be likely or unlikely, and so forth. So if they set equally likely, that's just going to produce a uniform CPT, which you can do by doing that. Okay, you can switch between this, if they're more comfortable with numbers. Yep. We can go restore or something. Oh, sorry, go to the advanced view. Sorry, so this is the view that most users would see. But if they wanted to, that's okay. Yep, cool. Yep, so we can switch across to numbers. We've already done a mapping to show them what those numbers are. They can never look at this if they don't want to ever look at it. There will be checks and balances as it's going through the approval process, but the individual user doesn't have to look at that. Okay, so they can switch between words and numbers, or they can go, if they're really comfortable with Bayes nets, they can just go off and look at the full table. And they can actually switch here between numbers and words as well, if it's a little bit easier for them to think of it in that way. There's one other quick thing which makes things a little bit quicker to enter probabilities. If you go back to show single question. Okay, so say for instance they want to say ignore, basically they think that fences or signage is irrelevant, and that fence is the key one that they want to elicit probabilities for. They can set signage to any and then just elicit, so it'll show you the two rows that it's eliciting at any given time, and you can just elicit for that state. So it chunks up the CPT, so you can elicit chunks of the CPT instead. And if you click continue, it'll go to the next chunk. So it'll go down to the next chunk so that you can elicit that one. Okay, so that's the elicitation of the probabilities. So not too bad, particularly for the time. You guys can do much, much, much better. Okay. All right, so once we've elicited all of the probabilities, we can then start looking at the behavior of the model. So if you switch over to what's called scenarios, that's something that's a little bit more familiar of a term for them. They see something which some of you would look at and you go, oh, that kind of looks like a BN, which they would just look at and think, oh, these are, just the status of various variables. Okay? They don't know what the linkage is. They don't know that there's, causal arcs essentially going this way. They don't know any of that, or don't need to. They can if they want to. But what they can do is look at this and say, okay, if we start adding evidence into here, so for instance, if we choose to add that we've got a fence, and we say, well, let's do a probability of it. So we've got uncertain information. So we've got, we think there's a 10% chance that somebody will put up a fence at some point. We can then do the reasoning, and it will update the probabilities elsewhere. And it's a very minor point, but you'll see that the bars are kind of progressively moving. This is the kind of things that you should be thinking about. So the fact that you can see them moving means that you go, I know these nodes are actually changing value. Okay, you know which ones are changing value. You don't have to go searching around for it. Okay, so it's not purely aesthetic. It actually has a function. Okay. Okay, so they can interact with this. If they see something here that they think is a little bit odd, they can go back to the model and start tweaking things and go back and forth at any stage. We've also got the similarity analysis. I think we can very quickly bring that up as a different presentation of information. Actually go back quickly. Yep, and just set, say, fence to yes, signage to no, and weed control to yes or something. Okay. All right. So they've got, so what we'll do here is a summary of what the impacts are. So we say, okay, here is what the evidence that we entered in up here for the report. We can say these are the probabilities that we started with. If we then, if we then did entered in the evidence that we had previously, this is the change in the probabilities for each of these. So these are the key kind of nodes that we're interested in: the status of all of the threats and the status of the species itself. And we can see the changes quickly, and it's basically sensitivity analysis, a very quick one. Oops. So if you scroll down a little bit, so this is sorted in terms of which ones have the biggest impact, which ones stay the same the most. So you can extract this kind of information, and for some people it will be useful, for others it won't be very useful at all. But this is some of the kind of reporting I think that you may end up doing for BARD. It may not be of this specific form, but there'll be different reports that you want to produce to give people an idea of what's going on in the model as well. So, okay. Okay, so yeah, so that's the basics of the ABCBN system. As I said, that was developed several years ago now. So we went through the planning on that in like 2010, 2011 or so. I think at the time it was probably, given the scope of the project and everything, I think it was quite useful that what we produced for them. They're still using it today, so obviously it's a usable system, and we've still got ongoing work with them as well for different training and so forth. So we know it's a practical system that people are using, can use, and do useful things with it. So I think it's a good example for that. The interfaces that you're going to create need to be a lot more advanced if we're going to get to a point where it's doing what we want it to do. It doesn't have to get there straight away. You can evolve it. That's the whole idea. But it will have to get to a point where it's making things very, very fluid, very, very quick for users. Okay. Oh, sorry, you've got that. Okay, so this is just slides basically describing what I described. Okay, so one of the things that the ABCBN model doesn't address is local structure very well. Okay, so you saw those CPTs. The experts had to go through and answer all of those CPTs. Now, we made that process as friendly as possible, but not as short as possible. Okay, so there's a lot of local structure in the ABCBN model that we could take advantage of. Usually the nodes are ordered, so we can make assumptions about how they impact on the child. Usually the interactions could be treated as independent in most cases, so you can simplify a lot of that process. And it might be an interesting thing to do, actually, to propose some of this work to them at some point. Okay, so what we're looking at now is the local structure for each of the nodes, basically simplifying the number of parameters that we have to elicit. Not the CPT per se, but the number of parameters that we elicit to be able to fill in the CPT. Okay, so one approach is elicitation by partition. So this is essentially what we were looking at in the ABCBN system, where we said a person could say any state of this is going to have the same distribution. 12, well, yep, okay. Okay. Yep. Okay, so one representation of it was what we had in ABCBN. This is another representation. We can have basically a tree classification. We can just show them the tree and not even show them the CPT. So we could say if A happens to be true, then we know it's a probability, this particular probability of the variable X is definitely going to be 1. So we've elicited 4 rows all at once, which is very useful. Otherwise, we can branch off to other nodes and then just elicit what we need to. So we don't need to elicit the value of C again, or A, or other variables here again. We can just say if A is true and B is false, I think it is, it's going to be 0. So it's these two down the bottom. Oh, sorry, A is false and B is false. It's 0. And then we can handle these individual cases. Maybe they're the most interesting ones, and we can just focus on those. Yep.
This is what we were doing with that any state.
That's right. Yep. Yep. So yeah. So the any state is one. It covers most of the cases that you would want to do with a decision tree, but I don't think it covers all of the cases. I think this is a little bit more flexible. Okay, so if your parents have independent effects on your child, as I was saying, you can simplify the elicitation process a lot. You can, for instance, if you've got a relationship that that looks like an or, an and, or an exclusive or, you can take that as the model and then add noise to it. And that's usually a very good representation. In fact, it's been shown to be an excellent representation in a lot of cases. And so this is a useful simplification that you can do. I'd imagine in these kinds of models, you would make quite a lot of use of this, actually. Okay, so let's focus just on noisy OR. Basically, the idea behind a noisy OR is you take a normal OR and you add some noise to it. So instead of saying that if one of the causes is true, the effect is definitely true. You say that if one of the causes is true, it's most likely that the effect will be true, but there's some chance that it'll fail and won't cause the effect. Okay, so, and you're making certain assumptions, lots of assumptions, but modeling in some sense is a lot of assumptions. So you're saying, okay, if cold causes, whatever inhibits cold from causing fever, for instance, so you've got various things that cause fever, say cold, flu, whatever else. Whatever inhibits cold from causing the flu, whatever prevents it from causing the flu, you're assuming is entirely independent of whatever causes flu, inhibits flu from causing fever. Okay, so you're assuming that the inhibitive effects between across all of the parents are all independent. And then if you assume that, you can summarize everything as just a few noise parameters. And you can, if you think about it, you can simplify things a lot if you do this. Okay, so here's a very quick example. We've got three parents, cold, flu, and malaria. And then we've got a child node, which is the fever, and we want to work out the probability of the fever node. So again, everything's binary, so just to keep things simple. Okay, so then what we do is we model the probability of not having fever. Okay, and we do, once we've worked out the probability of not having fever, then we can go back and calculate the probability that we do. So we can say, So we can say there's a 0.6 chance that a fever will be caused by cold. So if you've got a cold, there's a 0.6 chance that we've got fever. 0.4 chance that we've got fever. There's a 0.8 chance that we'll have a fever if we had flu, and there's a 0.9 chance that we'll have fever if we had malaria. Okay, and then we take the opposite of those, basically the chance that they'll fail to produce the effect, and we just include that in our noisy OR. And this makes the process a lot simpler, and I won't go through the process because we don't have a lot of time. But if you think about it, we just need to elicit one parameter. So we've got the 0.6, 0.2, 0.1 probabilities of failure, just for each parent. And then we've got one additional parameter. Okay, so if you've got 10 parents, which you may have, you shouldn't have, but you may have, and all of those are binary parents, then that would require 1,024 parameters. If you just elicit, if it's got a noisy OR structure, if you can identify that, then you just need to elicit the 11 parameters. And you can let them put in 10 parameters because it's actually quick to do the inference. Okay, but usually if you've got 10 parents, you've probably got the wrong model because there's interactions further up that you want to model properly, and so forth. But there may be some cases in which that's true, particularly if they're the same kinds of parents and so forth. Equations, which I won't go through in any detail, but which doesn't matter too much because you're not going to be using equations really. But equations are another way of capturing the local structure. Now they're actually an excellent way of capturing that local structure. The problem is you've essentially shifted the modeling problem to the development of the equation. So that's not very useful. Definitely not very useful here. Okay, so normally with an equation, you can obviously specify a model, a forward model with an equation quite straightforwardly. You could describe the same forward model with a Bayesian network. Usually if you've got a node, you can say, instead of specifying every possible CPT, you can specify an equation for that. We'll see some quick examples of that. The only problem with equations, so the only caveat that I would give for working with equations for this kind of model is that if you're eliciting different equations from different people, unless you're expecting the equation to be obvious, you'll get very, very different equations from very different people, and you'll basically have to resort to data mining to then get the combined, a combined equation from that. So, okay. If you can use equations with your experts, and a lot of experts are normally quite comfortable with using the equations depending on the domain, then it's fantastic because it reduces the elicitation burden immensely. It makes the underlying rules transparent. So CPTs can have the problem that it's just a big table of numbers, and to read any kind of structure into it, you have to then work backwards to see what the structure is. But the equations, if they're relatively simple, then you can usually perceive the structure very, very quickly. But sometimes the equations can hide the structure as well because they can get really complex. Okay, so you can use it to describe relationships for discrete nodes, continuous nodes, mixed nodes. You can use equations, obviously, to describe deterministic relationships, like physics equations, for simple systems. Or you could do a probabilistic relationship as well. So there's no real constraints on what you can do. This is an example of equation in Netica. So that would be the syntax. The different software has different syntaxes. I probably prefer Genie syntax the most. But Netica's is not too bad, and it has a very wide library of functions, which is quite useful as well. So in Netica, you would say that your position variable, so if you can imagine that you've got some position variable, I don't think I'll bring up the network, but you've got some position variable, you've got some start position, speed, and time variables. You're saying that the position variable is a function of these three variables, and that function specifically is this equation on the right-hand side. Okay, and this is what it would look like in Netica. Pretty much you just exactly the same thing. Okay, so in all of the BayesNets tools cannot deal with equations exactly unless they take on, well, there's some tools that can deal with equations that are of Gaussian form. But generally, if you want generalized equations, which are the most useful ones, there's none that can do exact inference with that. So you're always going to have to convert it to a CPT at some point. So you put in an equation to say what's going on, but then you convert it to a CPT. And the way that they do the conversion to a CPT is by doing a simulation. So they plug in different values and see what the effect is for a particular discretization. Okay. You can also, in most of the tools actually, just do the full inference stochastically. So you can say, you can start sampling at the root nodes, and then sampling at the child nodes, and then descendants and so forth. And most of the tools support that in some way or another. And usually if you're heavily working with equations, you want to stick to the stochastic simulations. Okay. So we saw an example before over here. So this is an example of a deterministic equation. Okay, so we're saying this is a deterministic function of these three variables. Over here, we're saying we've got a probabilistic relationship. So we're saying that rainfall, the probability of rainfall, is a function of the ENSO node. Okay? And then we can define that relationship over here. So we can say there's a normal distribution in which the value of the rainfall node, and you probably haven't seen values yet, but nodes can take on particular values. So you take the value of the rainfall node, that's not the probability, the value of it, and then that becomes the mean you take the value of the ENSO node, and then you calculate a mean, and then that becomes the mean of the rainfall node. This is why I don't like Netica syntax, because you keep repeating variables unnecessarily a lot. Okay. All right, so that's, so you can do computations like that and specify functions. Netica's got a huge library of functions, pre-built functions that you can put in, which is really useful. That's useful for continuous variables. If you've got it discrete variables, then pretty much your only useful kind of technique or function or operation is the ternary operator. So you guys are all programmers, possibly not C++, or Java or what have you, but I suspect most of you would have seen the ternary operator at some point. Yeah, so Netica supports that syntax. And you can just specify basically a whole bunch of if then else kind of conditions and fill in your CPT that way. So in some sense, this is a manual way to produce the decision tree representation. Okay, and you can do it for probabilities as well, and you can chain them down, so there's no problems with doing that. You can create constant nodes in Netica. So I don't know what's constant about them specifically because you can change the values, but essentially what that means is it's just some variable within the network that has a value. And you can change the value and you can use that variable wherever you would use any other kind of node. So for instance, you can create a false positive rate variable. You can give it a value of 0.02. So that just sits there doing nothing, not connected to anything in the network. It just sits somewhere there. And then you can use that in your equation. So for example, in here, so we've got some equation where we're trying to work out whether a person has used steroids based on the result of a test, like what we had yesterday. We can incorporate the false negative rate in that equation to simplify things and to document things better. So this is all, in that sense of documentation. Okay, we will not do this. I don't think we have time. Yep. There was if you want, at some point, as exercise, as a homework or whatever, there is a nice exercise there for equations, which is to model essentially genetic inheritance, and for eye color. So if you want to do that, it says there to build a 3-node network. I'd recommend actually breaking up the genotype and the phenotype. So you would build essentially a 6-node network where you say what the genes are doing, and then for each individual how that produces an eye color. So those phenotype nodes are going to be very simple, but it just tells the story a little bit better. But that's for you to do if you wish in your own time. Yeah, so we've got lunch now.